In the past, we keep saying that the stress tensor over here, or the matrix that describes the stress state of the system, is always symmetry. Alright, meaning sigma 1, 2 is the same as sigma 2, 1. So therefore, there are symmetry along this thing. Alright. Now, but we didn't actually prove to you, and therefore in this video we will prove to you in terms of 2D. Alright, in terms of 2D, so we can generalize 2D in terms of 3D later, but we just derive 2D only. Alright. Imagine we have a plane over here, and we have the basis vector. If you still remember, it's just some axis. We call this the x1 and we call this x2. Alright. The stress along x1 is sigma 1, 1. The stress along x2, it's sigma 2, 2. Alright. Shear stress is simply sigma 1, 2, meaning you take this plane over here and you shear it to this x2 direction. Alright, and therefore it will be sheared. Alright, sigma 1, 2. Now, we also have a a stress in terms of sigma 2, 1. Alright, so we take this x2 plane and shift it to the x1 direction. So we will shear it in this direction, or should be this direction, something like that. Alright, we analyze things in terms of static, meaning it does not move. Alright, the system does not move. It's equilibrium when it's equilibrium. It's like the conservation of energy. Summations of force is equals to 0. Alright, or summation of force minus ma is equals to 0. But since we have no acceleration, so therefore summation of force is equals to 0. Alright, so because we are static, alright, we are static now. So far so good. Since this is static, summation of force is equals to 0. Sigma 1, 1 that is over here, on the opposite side, alright, we will have a same sigma 1, 1. Alright, but instead of writing sigma 1, 1, I can write as sigma 1, 1 plus a small change of sigma 1, 1. It's still the same, alright, because if this is 0.0001, if this is 10, then the difference aren't that big. Alright, it's just trying to re-represent this thing. Or in other words, if you could say that I would apply certain, okay, never mind. So you just represent this first. Alright, let's represent that. So I didn't explain properly. This small change is really very small. It's near to 0, super near, 0.00000. You can go all the way. Alright, so no matter how small this thing is, this is way smaller. So therefore, we're just representing things in that manner if I didn't explain it properly. Right, so this thing, therefore, is somewhat equals to 0, but it is something over here. Alright, so we represent the small change of sigma 1, 1 as we can return this formula as this one. Alright, so this small change of sigma 1, 1 is simply the small change of sigma 1, 1 over here, and it's along the changes of x1. Alright, this x1 basis. Multiply, because this is in terms of stress. If you were to divide by the distance, you're going to have a force. But however, this is in terms of stress, and therefore we want to equalize the SI unit. Therefore, I multiply with a small change of x1. Alright, so in other words, if I cancel both of them, this is exactly the same as this one. Alright, so I'm just re-representing things and make things more a little bit expanded version of it. Alright, so therefore I can re-represent this as this. And therefore same goes to sigma 2, 2, the opposite direction. We simply do this and then this. It's the same thing as what we have done over here. Alright, instead of 1, 1, I write 2, 2. Okay. Same as for the shear stress over here, sigma 1, 2. Right, when you pull in this direction, we know that shear stress is pulling in both directions. Alright, so when I pull in this direction, for example, I'll have something that is opposite of it, because it's a static. Alright, meaning I'm not shearing it, I'm just simply re-representing this thing, alright, as its static force. Static equilibrium counterparts. Alright, so this force is different from this one because we are totally never moved. So we haven't sheared it anymore. We didn't shear it. We didn't actually shear it, right? So therefore, it's just simply this notation of sigma 1, 2, and that's it. But because it's static, we need a somewhat equilibrium force acting behind. sigma 1 2. Alright, and we likewise can also represent in the same form. Okay, before I continue to write this term, alright, is in terms of sigma what? It's going in which direction? Going in the x2 direction, right? Therefore I should write it over here as x2 delta x2. Alright, this is something that I need to do. So I didn't cheat your feeling, I keep everything the same. It's just I rewrite this thing as this thing. But just to take note that the direction of the basis is in towards x2. Alright, now same for sigma 1 2, we'll do for sigma 2 1. Sigma 2 1 is into the direction of x1, and therefore we'll write x1 over here. Alright, so this portion is sigma 2 1, this portion over here is sigma 1 2. Okay, and these are all stresses. This is stress. Alright, all stresses. Alright, they are all stresses because everything is so messy right now. But I just want to convey that these are all still stresses. Next thing, we're going to define summation of force is equals to 0. We know that summation of force is simply sigma is equals to force over area. Alright, if that's the case, then if it's dealing with forces, then we're going to take stress times area is equals to force. So far so good. And therefore, since we have all these stresses over here being described, alright, I'll just need to multiply by 8 so to get a force. Alright, so I can write in terms of equation. And therefore, this one is what I'll just copy. Alright, this stresses I'll just copy over here. This stress I copy over here. This stress and this stress I all copy over here. So these are all stresses. And simply label them. At least it is clearer for you to see, right? Next, how do I define this area? Alright, the area is somewhat perpendicular to the stress itself, right? I take the plane of 1, alright, meaning this plane over here. The forces acting on, the stress acting on this is stress 1 1, alright? And therefore the force that acts on this sigma 1 1 is the perpendicular area. And this perpendicular area is what? It's somewhat to the x2 direction, and we can call this some small values of delta 2 or delta x2. Alright, so this length itself is delta x2 multiply, because now we are talking about 2D, so if it's going into 3D, I'll just simply take this as 1. Right, so 1 times sigma x2 will still give us our area as sigma, not sigma, but rather than delta x2 in terms of meter square, for example. Alright, so in other words, I'm simply taking this plane, this is the area, right? It has a length of sigma, why I keep saying sigma, delta x2 times 1. That's the meaning of it. And therefore my area for sigma 1 1 is delta x2 times 1, which is delta x2. So therefore delta x2 for sigma 1 1 case. Now simply multiplied it into here, delta x2. Okay, same as for stress 2 2. Alright, stress 2 2 is this direction. Its perpendicular area is this area. Alright, and this length is simply in the x1 direction, and therefore it's some small delta x1 times 1. Alright, so the area is this. Alright, therefore I can rewrite things as x1. Okay, over here for stress 2 2. Now stress 1 2 and stress 2 1, they are slightly different. You remember, shear stress, its force, is indeed it's taking its instead of perpendicular area, it's taking its parallel area. Alright, previously our force is like this, right? But now, because it's a shear force, your area is in fact in the parallel system. And therefore what we can do is sigma 1 2, this is the area. Right, this is the area. And we have a length of delta x2 multiplied by 1. So this shear force is multiplied with this parallel area. Alright, therefore what we have is delta x2. Okay, now as for sigma 2 1, in the case we'll have go in this direction, right, the area. And therefore this thing is in terms of sigma x1, right? It's in the x1 direction times 1, right? So therefore the area is simply sigma x1. Write it over here. Okay. Now, in a bigger picture, sigma 11 is still here. Our area is simply the red one. Alright? And therefore what you have is a force in the 1 direction. I mean 1 direction. And similarly this one, alright, for this one will be a force in the 2 direction. And then as the rest. Alright? And summation of force simply is plus. Okay? And it's equals to 0 because the summation of force is equals to 0. So far so good. Since we say this is static, summation of force is equals to 0, the summation of moment, it should be also equals to 0. Alright, but how do we take the moment from, and how does this rotate, and where does the fulcrum, if you have a fulcrum, a seesaw, or the point where it turns, alright, where it turns, we need something of a point over here, right, this point. So therefore, in order to do that, we just plot this point over here. This is our fulcrum at O. Right, so I just write it as MO, summation of moment. And summation of moment is simply equals to force times its perpendicular distance. Okay? For example, if I have a force of sigma 11 times sigma delta x2, I think. This one is our stress, this one is our area, if you still remember. For example, because I didn't, sigma 11 can be represented as, this form. Alright, but I'll just simply represent this as this first. Alright, for convenience sake. So to show you only. So therefore this force over here is acting on this direction. Alright, and the perpendicular distance is this one. Alright, is this one. Hopefully you can see, it's this thick line over here. And you may wonder, my fulcrum is over here, why you take only this half? Because my force, alright, my force is acting on this side. My force is acting on this side, right? Am I actually gonna move this particular, so this point is here, so I mean this line is here, and I apply a force over here. So when you apply a force over here, definitely you would know that this line over here would turn. Alright? Because although the fulcrum is here, on the other hand, it is somewhat symmetry on the other side. You get what I mean? I don't know whether you can see it. Actually, I cannot see it also lah. But at least to the best extent is that the force itself is acting on this point. So therefore, when you apply the force to its perpendicular distance, you definitely turn this thing over here, and this is it lah, right? Okay, and therefore this line is in the delta x2 direction, right? It's in the x2 direction. So if it's, so the stress is acting and the force is acting in the middle of this thing, and therefore I'll divide it by 2 is my perpendicular distance. Alright, so therefore I'll just multiply by delta x2 divided by 2. I can simply sub it into my forces over here. But because this is one big chunk of stuff, I'll just try to do things up. I simply rewrite that long chunk, alright, the rest of the stuff I'll simply re-put over here. Alright, so it's easier for us to see. And we know that at the force 1, 1 area, meaning going in this direction, the perpendicular distance is this distance, delta x2 over 2. So I can simply multiply that in over here. Alright, now as for sigma or force 2, in this case force 2, you apply it at this point. So you're gonna rotate this line over here. Alright, so and this line is in the x1 direction, delta x1 I would say, and therefore delta x1 divided by 2. Same thing. Okay. Now, as for the shear stress sigma 1, 2, your force is acting over here, sigma 1, 2, going in this direction. Alright, and therefore this fulcrum, now I know where it comes from, is for the shear stress. Alright, so this applied force is straight away this thing. So your force multiplied by its perpendicular distance, which is this distance, and this distance is simply none other than delta x1, the full distance. Alright, and therefore I can write over here as delta x1. This is for force 1, 2, right? Force 1, 2 is this one. It's this one. So I didn't cheat your feeling. Okay, as for sigma 2, 1, you're actually applying the force in this direction, force 2, 1, and therefore it's this line. It's this line, sorry. You're applying the force in this direction, so its perpendicular distance is this one, so you're going to rotate in this manner, right? Because you're applying the force in this manner, if you can see, so you're actually rotating. Therefore we can simply write delta x2 over that a delta x2 will do, because it's just this line over here, the perpendicular distance. Alright, and therefore I can, because this is already a lot of stuff, because this whole chunk is very big and very don't know what the hell, so therefore I just write in terms of their colors. Alright, force 1, 1 is simply this one times its area, delta x2 in red, and then perpendicular distance in our case over here. Alright, so I'll just simply write in terms of their names, at least you know where are they coming from. Alright, and now the most tedious parts come in. You're gonna multiply all this constant into the bracket. Alright, so I'm gonna take in these values and multiply inside both of them. Alright, and I'll not go through with you, so I'll just do for you. When I expand, I'll have all this stuff over here. So I still indicate in terms of their colors, so at least you can see properly that I actually multiply them into our systems. Alright, I didn't cheat your feeling for any case. So I forget one very important part is the direction of the rotation. Alright, the direction of the rotation for the moment is going in this direction is plus. If it's going into direction, this is minus. Anti-clockwise is minus, clockwise is plus. Should be? Okay, never mind if that's such the case. Alright, so as we can see that the moment for sigma 1, 1, alright, is going in this direction. Right, when you pull sigma 1, 1, there will be, the force 1, 1 I would say, you go into this direction. And if you were to go in this direction, this means that you are going in the, I should draw wrongly, should be like that. So the anti-clockwise direction is minus. Alright, so for a force 1, 1, alright, and its moment, we should have changed it to a minus sign. So the whole thing is minus over here. If I were to multiply this minus in, alright, what I'll have is, so I remove the bracket now. Alright, I have minus times minus is plus. This is for the first case. Next case, so for force 2, 2, or if this is force 2, 2, the fulcrum is over here. So when you, now I also find that the reason behind why this fulcrum is useful already. So when you pull in this direction, alright, this is the delta, actually in fact this should be delta x1 divided by 2. It's not this one. Alright, just now we say that we are rotating here. No, okay, because the fulcrum is over here. So we're going to rotate in this manner. So therefore, if we are rotating in the anti-clockwise direction, it is also minus. Alright, so it's minus and plus. Okay, and in fact from here I would finally understand fully why the fulcrum is so useful. Alright, and such that I would actually remove the minus sign over here. Right, and I'll explain to you why. Okay, just now I explained to you that sigma 1, 1 over here, this is the force, maybe force 1, 1, alright? The fulcrum is on this side. So if I were to apply the force, you're going to go rotating in this manner. Because the fulcrum is over here, you're going to rotate. Alright, so therefore this is the purpose of the fulcrum finally. Alright? And therefore, and therefore this is the delta x2 divided by 2 type of thing. And therefore if you are rotating in the clockwise direction, this means it's a plus sign. Alright, I hope that this is pretty clear now. Force 1, 2 is going in this direction, right? Because you're pulling this with a certain distance over here, and therefore you are rotating in this anti-clockwise direction, which is minus. Alright, if it's minus, then I'll just simply write this stuff as minus. Okay, now sigma 2,1 or force 2,1 now, sigma 2,1 times area is force 2,1, and then I'll just rotate in this manner, right, because I'm pulling in this direction. So rotating in this manner is a plus sign, and therefore I have all this over here, right? So we have removed the brackets and putting in the signs, the V, the plus minus, things like that. Now, if you take a look, this term over here, there is 3 times delta x. This one is 2 times delta x, if you take a look, the degree. Alright, so for example, 0.001 times 0.002 times 0.003, and now it will be a very, very small number comparatively to this one, alright, because it's 0.002 times 0.003. So at least at a certain degree, this degree is somewhat still have a larger number than this form over here, because it's third degree multiplication. So therefore, we can simply assume, not assume, but rather we can straight away know that this whole thing is simply 0 compared to this one, because it's way smaller. So I can cancel this term. Same as the 3 terms over here, I can cancel them. I can cancel them for over here, and I can cancel them over here. So far so good. Because they are all simply 3 degrees of the delta, all is very, very small compared to its counterparts, which is in terms of 2 delta x. Alright, you see? These are all 2 times delta x, these are all 3 times delta x. So comparatively, they are all lousy. Alright, I mean all goes towards 0. Alright, and therefore we have cancelled out all this, and we have all this left. Alright, and I'll simply translate all this that is left over into this final equation over here. Okay, and what can we deduce from this final equation? If you take a look, sigma 1, 2 and sigma 2, 1 over here, I mean this one and this one, they share the same area. Right, they share the same area in terms of the shear moment. Alright, since they are sharing the same area, this means that actually they will cancel out each other. Right, for example, if you have a certain shear stress, maybe this is the cube itself, delta x2, this is delta x1, correct? And they share the same piece of area over here. So stress 1, 2, for example, minus stress 1, 2 is going in this direction, stress 1, 2. Okay, and that stress 2, 1 is going in this direction. But because they share the same area, they somewhat cancel out each other. As you can see, because this is minus, this is plus. Alright, this is plus. So because they share the same area, the same constants, and therefore to a certain extent they are actually related at the same plane. Or in other words, sigma 2, 1 is equals to sigma 2, 1 is equals to sigma 1, 2. Alright, I think this is a better explanation. Sigma 1, 2, alright, is put times it's in the direction of force 1, 2 also, right? So it's going in the rotation manner over here. Alright, it's going in the rotation manner due to this fulcrum. Alright, while sigma 2, 1 is over here, or force 1, 2 is over here, it's going to rotate in this manner. So the summation of this moment, as you can see, they actually cancel out each other at somewhere over this point or whatever. Alright, so I think this is a more better explanation than just now what I've said, because in terms of area, yeah, there's no meaning, but in terms of moment, then something is there. Alright, and therefore, so therefore they can actually cancel each other, as we know, because of such of the meaning. For another explanation, you can also say that sigma 1, 1 and sigma 2, 2 will never be the same. They will never be equal. Alright, because they are going in the different directions. This is x2 square, this is x1 square. Right, they are going in both directions, and therefore they shouldn't be equals. and therefore what should be equals is this thing. You can take that as that particular meaning. Alright, so this thing should be equals to 0, and therefore sigma 11 minus sigma 22 is also equals to 0. And if such the case of that happen, then sigma 11 is equals to sigma 22 for in terms of their magnitude. Alright, not in their directions, because it's 1 1 and 2 2. Alright, the one direction and the two direction, if you were to say so. Alright, so I hope that this is pretty clear, although this is a little blurry here and there. And therefore minus sigma 1 2 is equals to a plus sigma 2 1 is equals to, or another is equals to I can actually bring this over to the other side, and therefore what I will have is 1. Alright, and we know that sigma 1 2 it can be written as sigma ij, and therefore is equals to sigma ji. So we have somewhat go through all this and derive this equation over here. And I shall see you in the next video for other stuff.